Welcome back to AI Talks with Chris and Nita. Ready for another deep dive?
Absolutely. Always ready to dive in.
Awesome. So today we're looking at something called radial basis function neural networks.
RBF networks.
Yeah. RBF networks, much easier to say. Our listeners sent in some research on these. They seem like this pretty specialized type of artificial neural network, right?
Yeah, that's right. They're really good at certain tasks, especially things like function approximation, which is basically like, predicting a value based on some input data.
Okay. Cool. So let's break this down. What exactly are RBF networks?
So think of it this way. They're like a specific type of ANN, like a special flavor, And what sets them apart is their structure. They have these 3 layers. Each layer does something pretty unique.
3 layers, huh? So like a cake.
Haha, kind of. You've got your input layer, the hidden layer, and the output layer.
Okay, so the input layer, that's where the data goes in, right?
Yeah, exactly. Like, let's say we're trying to predict house prices, right? The input layer would take in all the info about the house. Square footage, number of bedrooms, location, you name it.
Got it. Then it goes to the hidden layer.
Right. Now, the hidden layer is where things get really interesting. This layer is made up of what we call RBF neurons.
RBF neurons, okay. And what do these RBF neurons do?
Well, they act like sort of prototypes. Each one represents a kind of typical example from the data that the network was trained on.
Prototypes. So like in our house price example, each prototype would be like a specific house with its own set of features and a known price.
Yeah, exactly. So let's say a new house comes on the market. What the network does is it takes the features of this new house and it compares it to each of those prototypes in the hidden layer. It basically figures out, how similar this new house is to all the examples it's already learned from.
So it's like it's measuring the distance between the new house and all the prototypes.
Right. It's calculating how close or far away it is from each prototype in that house feature space.
Interesting. Okay, so we've got these distances, right? But how does the network actually use those distances to predict the price of the new house? I mean, where does the radial basis function part come in? That's been bugging me.
Good question. This is where the math gets a little funky. These distances, right? They get passed through a special mathematical function. Usually it's something called a Gaussian function. And that function, it transforms those distances into something called activation values.
Activation values.
Yes. Think of it like each prototype is shouting, hey, this new house is a lot like me, or nah, we're totally different.
So like the closer the new house is to a prototype in that feature space, the louder the prototype shouts.
Haha, yeah, something like that. The closer the match, the stronger that prototype's activation. And the stronger the activation, the more influence that prototype has on the final prediction.
Okay, starting to get it now. So we've got all these prototypes, each with their own activation level, depending on how similar they think the new house is to them. But how do we get from all these different activations to a single price prediction?
That's where the output layer steps in. It basically takes all those activation values from the hidden layer and it kind of combines them. Think of it like a weighted sum.
Weighted sum. So each prototype gets a vote on the final price. But some prototypes get more say than others.
Exactly. The prototypes that have been really good at predicting prices in the past get more weight. Their votes count for more.
That makes sense. So prototypes that keep getting it right get a bigger say. But how does the network figure out which prototypes are the reliable ones?
That all happens during training. The training process is how the network learns and fine-tunes itself to make accurate predictions.
Okay, let's talk about this training then. How do you train an RBF network?
Well, there are 3 main steps. First, you got to choose where the centers of your radial basis functions will be. Those centers, they're like your prototypes, remember? Right. So choosing those centers carefully is important. It can really affect how well the network performs. Sometimes you pick them randomly, but there are also algorithms you can use to try to find the most representative data points.
So you're saying where you put those prototypes in that data space matters a lot.
Totally. Then, step 2, you have to figure out the spread parameter for each of your prototypes.
Spread parameter, what's that?
It basically controls how much influence each prototype has on the area around it. A wider spread means the prototype has a bigger sphere of influence.
Got it. So a prototype with a wider spread would consider more data points to be similar to it.
Exactly. Like, imagine those prototypes are like little magnets. A wider spread means a stronger magnetic field, so it pulls in more stuff.
That's a good way to think about it. So first, you choose where to put your prototypes, and then you adjust their magnetic field to control how much influence each one has, was the third step.
Okay, so the third step is where you train the output weights. This is all about refining those votes we were talking about, making sure that each prototype's contribution to the final prediction is just right. It's like fine-tuning an orchestra, making sure each instrument is playing at the right volume.
Cool. So you're adjusting how much each prototype's vote counts towards the final prediction. That's really interesting. So let me try to summarize this. You feed data into the network, it gets compared to these prototypes in the hidden layer. Then those prototypes, they kind of vote on a prediction based on how similar they think the new data point is to themselves. And then the whole thing is like fine-tuned during training so that those predictions are as accurate as possible. RBF networks, they make this like complicated process feel almost intuitive. But I got to ask you one last thing before we wrap up.
Sir, go for it.
How much is changing those spread parameters, those magnetic fields, how much does that affect the final predictions of an RBF network? I'm really curious about that.
That's a great question. And honestly, it can have a huge impact. The spread parameter, it really determines how much each prototype reaches out to influence nearby data points. Too narrow, and the network might miss important similarities. Too wide, and it might overgeneralize. It's a delicate balance. But hey, that's what makes RBF networks so fascinating to study. There's always more to explore and tweak.
Absolutely. Well, on that note, we've got to wrap up for today. But to all our listeners out there, I'd say this. If you're intrigued by the idea of these voting prototypes and how their influence shape predictions, then dive deeper into the world of RBF networks. It's a rabbit hole worth exploring, trust me. Thanks for joining us for this deep dive, and we'll catch you next time on AI Talks.